Welcome back to The Explainer. Today, we're stepping into the incredibly secretive, mathematically staggering world of semiconductor manufacturing. If you've ever looked at a modern CPU and wondered how humans actually construct something at the atomic level, you're in the exact right place. We're going to break down an impossibly complex 940-step microchip fabrication process and distill it into a logical, highly structured systems engineering loop.
Okay, let's dive right into this. We've got 5 main parts to cover today: the scale of the challenge, the 6 categories of fab tools, photolithography, the deposit and etch cycle, and finally, wafer testing and packaging.
Part 1. The scale of the challenge.
Check out this number, 90 billion. A single modern smartphone holds 62 microchips containing a staggering 90 billion transistors. To mass-produce architecture at that kind of volume, you need a specialized factory. We're talking about a clean room environment spanning the area of 8 entire football fields, processing silicon wafers over a 3-month continuous period. It's just massive.
Now, what's really interesting about this is the physical size of what we're actually building here. The FinFET transistors at the foundation of these chips, they have a pitch of just 57 nanometers. To put that into perspective, that is completely dwarfed by a single dust particle or a human hair. Even a biological mitochondria is huge by comparison. We are literally engineering cities of logic gates at a biological scale. So if you're trying to wrap your head around this, keep this analogy in mind. Visualize this whole process like baking a cake, but it's a cake that is 80 layers tall with a recipe demanding 940 exact steps, taking 3 full months to complete. And get this, if any single measurement, bake time, or temperature is off by just 1%, the entire cake is totally ruined.
Moving on to Part 2, the 6 categories of fab tools.
So how do you avoid getting completely lost among the 435 multi-million-dollar tools sitting on that clean room floor? Well, as a systems engineer, grasping this beast requires categorization. You've got to group them into 6 core functional buckets: making the mask, adding material, removing material, modifying material, cleaning the wafer, and inspecting the wafer. Basically, everything happening in the fab is going to fall into one of those 6 buckets.
Let's look at how these functional categories map directly to highly specific technical processes for our 300mm silicon wafers. Adding material involves deposition processes like PVD and CVD. Removing material relies on chemical or plasma etching and planarization. Modifying material uses ion implantation. And inspecting the wafer is done through precise metrology, usually using electron microscopes to hunt down nanoscopic defects.
And this brilliantly illustrates the extreme contrast in how these tools actually operate. Deposition, adding the material, is relatively gentle. It's kind of like spray painting a thin layer through a stencil. But ion implantation, modifying the material, is violent. It hurls atoms deep into the silicon lattice. It's literally like a cannon launching a baseball into a concrete wall, just to create those necessary P and N regions for the transistors.
All right, Part 3. Photolithography and patterning the wafer.
This right here is the absolute critical path for patterning incredibly small interconnect layers simultaneously across the 230 individual CPU chips sitting on a single wafer. The secret sauce for this mass replication is the photomask. Think of it as a 6x6-inch master stencil holding the exact design of the layer you want to pattern. Because they have to be so ridiculously precise, they cost about $300,000 each. Ultraviolet light shoots through this mask, and a series of lenses shrink or demagnifies the pattern by a factor of 4, projecting a flawless, nanoscopic image right onto the silicon.
Let's move to the next step and see how this builds a patterned layer step by step. First, we spin coat the wafer with a light-sensitive photoresist and soft bake it. Second, we expose it to that UV light through our photomask stencil. Third, the wafer goes into a developer to wash away the photoresist that got weakened by the light. And fourth, a hard bake solidifies what's left. Boom, we've just created our temporary stencil right there on the chip.
Now, the scale of repetition here is absolutely crucial. A single 17-metal layer CPU requires exactly 80 separate visits to the lithography tool. Yeah, 80. That means 80 unique $300,000 photomasks are used sequentially just to print the complete 3D structure of a single chip design. Insane, right?
Which brings us to Part 4, the deposit and etch cycle.
To physically build up that vast labyrinth of metal wiring and insulating layers on the chip, you really shouldn't try to memorize 940 linear steps.
Instead, like our source points out, it's way more effective to visualize the steps as a circle, kind of like a clock. The wafer just continuously cycles through, adding material, removing material, cleaning, and inspecting, over and over again, layer by layer.
A super vital piece of this continuous clock is CMP, or chemical mechanical planarization. This is a removing material step. By applying a specialized slurry and using abrasive pads, the tool physically grinds and polishes the top surface of the wafer so it's perfectly flat. And you have to do this, because if you don't level off the current layer flawlessly, the optics for the very next layer's photolithography will completely fail.
So, let's walk through one full macro revolution of this cycle, which is what's required to manufacture a single metal interconnect layer. Step 1. Deposit your insulating silicon dioxide. Step 2. Pattern the mask via lithography. Step 3. Use a plasma etcher to remove the exposed oxide down to the vias. Step 4. Strip the mask and clean the wafer. Step 5. Deposit copper metal to fill in those etched patterns. And finally, Step 6. Level the entire surface perfectly flat via CMP. The clock resets, and we are ready for the exact same thing on the next layer.
Finally, Part 5, Wafer Testing and Packaging.
I want you to really think about the concept of yield here. Ask yourself, what happens when a single stray nanoscopic dust particle or a minor photomask defect ruins just a few transistors on an otherwise fully functional CPU die? Well, this is exactly why those continuous metrology inspections and ultra-pure water cleaning steps we talked about earlier are so fiercely critical to the entire operation.
But here's the kicker. A damaged chip isn't always thrown in the trash. The semiconductor industry uses a pretty clever categorization system called binning. If a section of the integrated circuit is busted, the manufacturer just disables that broken section and sells the chip at a different performance tier. So an Intel chip coming off the line might be sold as a premium i9, or it might get downgraded to an i7, i5, or i3, strictly based on the number of surviving functional cores. So the crucial point is the staggering value added by this whole cyclic engineering process. We start with an incredibly delicate blank silicone wafer that costs about $100, but by running it through this 3-month systems engineering loop, it's transformed into a populated grid of processors worth roughly $100,000. That makes this manufactured silicon quite literally 10 times more valuable than its exact weight in gold. We've explored an absolute engineering marvel today, but it is still bound by the laws of the physical universe. So I'll leave you with this. As we continue to obey Moore's law and attempt to scale past a 57-nanometer pitch, what physical and atomic limits will eventually break this recursive deposit and etch cycle? At what point does physics just flat out refuse to let us shrink the stencil any further? Think on that, keep learning, and I'll catch you on the next explainer.